last time. All right, well, last time we proved the 5 lemma. Right, and so although we proved something more precise, the way you usually use this is that if these arrows are isomorphisms, the rows are exact, and the diagram commutes, then this one is also an isomorphism. Right, and we use that to see that if you have a space with a delta complex structure, and you compute the homology groups using that delta complex structure, then you get the same groups that you do using just singular chains. Right? Here's an easy corollary, again using the 5 lemma. Let's say that A is a sub-delta complex. Right, so A is a subspace, and the delta complex structure of X restricts to a delta complex structure on A. Then, well, you have a long exact sequence in the delta complex structure homology, so the simplicial homology. And you have the long exact sequence of the pair in singular homology. The inclusion of the chain complexes gives you maps like so. And since we've proved last time that this is an isomorphism and this is an isomorphism, right, then the remaining arrows have to be isomorphisms by the 5 lemma. Right? So by the 5 lemma. Right? So that's an example of how the typical use of the 5 lemma. Okay. So that's what we did last time. Questions on last time? Yes?
More of a comment, but the top row is all simple.
That, oh, thank you. Yes. Thanks. More questions?
I have like a logistical question.
Sure.
So are we going to have a practice midterm over break?
Yes. Yes. So hopefully tomorrow I'll have a chance to write a practice midterm and I'll put that up.
And will there be any assignments due before the midterm?
No.
Okay.
Yes.
This is a non-logistical question.
Uh-huh.
So what happens to this chain, or this long exact sequence, or this pair of long exact sequences on the low end when we're looking at 0 and then something just goes to the 0 group? In other words, do we still get enough structure there for the 5 lemma to apply to like H0
Sure.
of XA?
Yeah. So I mean, another way where you use the 5 lemma is if you have zeros. You know, if you were looking at, let's say just here. No, not X. X and A. Right, and so we have this, and then we have zeros. So we want to show that this arrow is an isomorphism. So we have this one, and then we have the one before it. Well, you can put a trivial arrow between zeros, and then you can continue this with zeros. and put another trivial arrow.
Okay.
And these are obviously isomorphisms, so that one is.
Got it.
Yeah. Yes, very good. More questions? Okay, so wonderful. So this isomorphism, then if you think way back to when we started talking about singular homology, we noticed that there are obvious pros and cons for each one. For example, it's obvious that this one is a homeomorphism invariant. So now we know this one is too, right? And it's obvious that if you have a delta complex structure with finitely many simplices in a given degree, then this is a finitely generated abelian group, and hence this one is too. So speaking of finitely generated groups, let's give this a name. If the rank of Hnx is finite, we call it the nth Betti number. Of x. And if you think way back to the first class, we talked about how Betti was one of the people who made progress in topology between Riemann and Poincaré. Great. So, and actually while I'm at it, so also the rank of an abelian group, as you know, so the rank of this, one way to think about it is that it's the dimension over the rationals if you take this and tensor with the rationals. Right? So you just get rid of all of the torsion and just look at how many copies of Z you have here, which become how many copies of Q do you have over here. And we mentioned the Euler characteristic the first day. So let me go ahead and define it. This is the sum, the alternating sum of the Betti number. So let's call this beta n of x. It is. So this is known as the Euler characteristic. And from what we've shown, it is a homotopy invariant, right? Because the singular homology groups are homotopy invariants. And if to connect this back to how you might have seen the Euler characteristic before, let's say that we have a if X is a polyhedron. So delta 0 of X is the vertices, delta 1 of X are the edges, delta 2 of X the faces. And of course, I mean the free abelian group on the vertices, free abelian group on the edges, free abelian group on the faces. Then, and these are finite, you can show that the Euler characteristic, so once you pass the homology, you get the same Euler characteristic as before you do. So in this case, this would be the number of vertices minus the number of edges plus the number of faces. And if you've seen the Euler characteristic in other courses, this is probably how you saw it. Yes?
When you write dims of Q, what does that mean?
This is a vector space over the rational numbers. And so, I mean, it's dimension. OK. Great. So let's see some applications. Yes?
So presumably the Euler characteristic is only guaranteed to be well-defined for spaces with finitely many homology groups?
Yeah. So I mean, we're defining it like this when this makes sense.
I guess
Right, so-
finitely many non-trivial homology.
Right, and finitely generated.
Right. that-
Yeah, exactly. So whenever this makes sense, if these numbers are all finite and there's only finitely many of them, then this is the Euler characteristic. Yes?
Can you say again what we mean by the rank of HN?
Sure, this is what I mean. So, Hn of x is always an abelian group, right? So you can, if it's finitely generated, I can always write it as c raised to some power times, and then c to the p1 to some power L1, cp2, L2, cp m, Lm. Right, so every finally generated abelian group can be written as a product of cyclic groups, right? So the rank is just this k. It's how many copies of Z do you have? Sure. These guys are known as the torsion coefficients. So they're also homotopy invariant. Excuse me. Yes?
Could you explain what that symbol in between H and
This tensor? Sure, this is a change of coefficients. So I have two rings, and I can tensor them together and get another ring. I can tell you very precisely what it means here. If this is what Hnx is, then Hnx tensored with Q is Q to the K. Okay, so when you tensor with Q, you allow multiplication by rationals. And if you have something that's a finite order, then I can always multiply it by 1, which I write as P1 over P1, and then I move one of the P1s over, and I kill it. So if I tensor with Q, I kill everything with finite order. Okay? But in any case, don't worry about it, because we're not going to use tensor powers very much at all. So if you like, it's just this. You just take the free part of characteristic 0 and turn it into a field. OK, great. So if you recall, one of our applications with the fundamental group was to show that the sphere was different from the circle, and different from, well, the circle was different from the sphere and different from spheres of arbitrary order, right, up to homotopy. So, well, now that we have homology, we can do this more generally, right? So, for example, we know that Hn of Sm, let's put a tilde, this is Z if n is equal to m and 0 else. So Sn homotopic to Sm if and only if n is equal to m. If you have, say, Rn, so if Rn is homeomorphic to Rm, then n is equal to m. Right? So notice, of course, here I can't put homotopic, because, of course, they're all contractible. So they are homotopic, right? But they're not homeomorphic to each other, right? And so, well, if they were homeomorphic to each other, then Rn minus a point would be homeomorphic to Rm minus a point, right? So you have a homeomorphism. You restrict it here, you end up here. But these are homotopic to Sn minus 1 and Sn minus 1. And hence, n is equal to m. Right. More generally, we have a fact that's called invariance of dimension. Right, which this is the first instance, but this works more generally for manifolds. So I've mentioned manifolds before. Let me remind you, an n-dimensional manifold is a topological space M, which is Hausdorff. Second countable, so its topology has a countable basis. And it is locally homeomorphic to Rn. Okay, so of course, typical example, like if you have a torus, then near each point you have a neighborhood that looks just like a neighborhood of the origin in the plane. Right? It's homeomorphic to a neighborhood of the origin in the plane. Right? So it's just like when you're on the Earth. If you don't think too much about it, you could think that it's flat because when you look around, it looks flat. Okay, so here's an interesting, for any space, not necessarily a manifold. The local homology at a point is the homology of x of the pair x and x minus a point. That point, that same point. If you have a manifold, so let's say an n manifold to mean an n-dimensional manifold, then the local homology, let's use HK, I can use excision to write this as Hn, where here P is a point in M and U is a neighborhood of P homeomorphic to, say, a neighborhood of 0 in Rn. Yes?
What do you mean by local homology?
The definition. The local homology is this. Yes. Uh-huh. Okay, but since U is homeomorphic to a neighborhood of 0 in Rn, I can think of U as being a neighborhood of 0 in Rn. And then I could use excision again to get that this is Hn, Hk of Rn minus a point. Right? Okay, but Rn is contractible, so this is easy to compute by the long exact sequence of a pair, right? So in the long exact sequence of Rn minus the origin, you would have Hn of Rn mapping to Hn Rn minus a point mapping to Hn of the pair. Wait, no. Hn of mapping to Hn minus 1.
And do these n decays?
They probably should. Thank you. So because this is contractible, and let's put tildes. Because this is contractible, these are always 0. And Rn minus a point is the sphere, is homotopic to the sphere. So this is Sn minus 1. So hk tilde, well, I don't need the tilde here, is equal to
Can you explain why that is?
Sure. So this is a pair, so it has a long exact sequence in homology, right? Rn is contractible, so its homology groups are just 0. And then Rn minus a point is homotopic to the sphere, right? Rn take away the origin, that's just a sphere. Okay, so for any manifold, the local homology is given by z if k is equal to n and 0 else. So we conclude this theorem, invariance of dimension, if M and N are homeomorphic manifolds, then the dimension of M is equal to the dimension of N.
What does it say after theorem?
Invariance of dimension. Yeah. Yes.
So is the local homology of the manifold at some point on the manifold, that's looking at k-dimensional holes in the manifold?
Oh, so by excision, it's looking at what does the manifold look like near the point. So it's checking. So on a manifold, you always locally look like Rn, and local homology is local. So it only sees what's going on near the point, and so it's like being in Rn. So if you like, local homology is going to detect singularities for you of a space. If you have a space that looks like manifold pieces, but the pieces have different dimension. For example, if you have a space with singularities, like conic singularities or a wedge, you could think of a whole family of conic singularities, then the local homology of that space would tell you where something had changed, right? Where it stopped looking locally like Rn and now it looks locally like Rk, or something like that. Yes?
So why do we get as our conclusion, in this theorem, why do we require M and N to be homeomorphic and not just homotopy equivalents?
Right. So, for example, if you think of Rn and Rm, they're both homotopic to a point.
Right, but I guess what I'm asking is where does this proof require it to specifically be a homeomorphism?
Well, so if our map were take Rn and map it all to a point, then when I subtract a point from the left-hand side, I get nothing on the right-hand side. Right? If you look at our proof for Rn to Rm, we had this map, and it restricted to a map once we had removed points, right? But that won't work if you're just projecting to a single point.
So homology itself is invariant under homotopy equivalence, but the operation of removing a point isn't.
That's right.
And that's the key. Okay.
Yeah. Okay. This was proven originally by Brouwer, our good friend who did a lot of things in topology and then decided that it was all wrong because he used the law of excluded middle. And they didn't really understand manifolds back then, but for him it was all about open subsets of Euclidean spaces and the fact that the dimension of what Euclidean space you were in was a topological invariant was a big deal. Right? Because it's really hard to prove this directly if you don't use homology or something like that. However, it wasn't homology that he used. Right. He used the degree of a map. Okay, so let's look at Sn. Well, let's say it like this. To every Okay, so to every map between spheres of the same dimension, we're going to assign an integer called the degree of the map. And the way we do this is we know that F induces a map between the homologies. And these are both the integers. Right. Every map, every homomorphism between the integers and the integers is given by multiplication by an integer. Right? That integer is the degree. So, so HNF of 1 is equal to some integer times 1. Is there name? Yes.
This Hn of f is the same as f.
F star, yeah, F star just restricted to the nth homology. Sorry.
Wait, so what is that one? I'm confused about what you wrote on the last line.
Yeah, so you have the integers.
Yeah.
So take 1, the integer 1, and see where you map it to. You map it to a multiple of 1, right? That is the degree, that multiple is the degree. So you might worry that how do I know which one is 1? Right, because the integers have 2 generators, 1 and minus 1. So how do you know whether you got a multiple of 1 or a multiple of minus 1? Right? So that means that you'd really like to have a choice of generator for the homology of the sphere. And we do, because as we saw right over there, but we had seen before, we can write the nth, let's go ahead and put a tilde, homology group of sphere as the nth homology of, that's not what I mean, of the n simplex relative to its boundary, right? And we have a preferred generator, right? So recall this is generated by the identity map. Okay, so we have a preferred generator, and that's what we use to talk about this. So you compare the image that you get by mapping that generator to the generator itself, and that's how you get this integer. Right? Yeah. So really, this just means we're picking an orientation on Rn, but we're picking the usual orientation. So you're putting this in Rn plus 1 with the usual orientation and choosing the generator there. And so if this map preserves orientation, this will be a positive integer. And if this map reverses orientation, this will be a negative integer. Okay, so there are several obvious properties of degree, and then there are some non-obvious properties. So let's list these. So first, the degree of the identity map is equal to 1, right? Because, of course, the identity just induces the identity.
So in short, can we say that the degree is, first off, the sign is determined by whether or not it switches orientation, and then the absolute value is, if we take a look at this map, the index of the image.
We'll get to that, but
Okay.
sort of, yeah. So almost everywhere, yes.
Well, I mean, if
But
we,
we'll get there,
Okay.
yeah. Okay, so another obvious property is that if f is not surjective, then the degree of f is equal to 0. Right? So why is that? If you can pick a point that's not in the image, then f factors through, so I have Sn, and f actually maps this to Sn minus this point, and then I can map that down to Sn. So if I look at this in homology, well, let's go ahead and put n. So I have here the inclusion, and no, I have here f, and here the inclusion, and here f. Right? So if there's some point that's not in the image, then f actually maps Sn to Sn minus that point. Right? And the map from Sn to Sn factors through mapping to Sn minus that point and then including it to Sn. Right? So this is a commutative diagram. And so this is z, this is z. But this, if you take the sphere and remove a point, then of course it's contractible to, say, the opposite point. Right? So this is 0. Let's put a tilde, and then I don't need to put any special cases. Right? So f star factors through the 0 map. So it must be 0. Okay. Next, if f is homotopic to G, then the degree of f is equal to the degree of G. Okay. It turns out, and we'll prove next semester, that the opposite is true as well. This is an if and only if. It's a theorem of Hoff. Right. So what this says is, what Hoff's theorem really says in today's language is that pi n of Sn, right? So the homotopy classes of maps from this n sphere to itself with a base point is the integers. And you assign to each homotopy class of maps, you assign the degree of any representative. Right? It's well defined because homotopic maps give you the same degree. Yes?
I don't know if we're still doing more properties, but when we're done doing properties, could we look at an example maybe of?
Yes, definitely. So let's go ahead and look at an example. So if you're going from S1 to S1, right? So view S1 is sitting inside the complex numbers, and look at the map C goes to C to the K. Okay? So once we develop more theory, we'll be able to show that the degree of this map is k, right? So you should think of the degree as telling you how many times you wrap around, right? So very clearly here in the case of S1, but it turns out also true for other spheres. We're really looking at how many times does this map wrap the sphere around the sphere when you take orientation into account. So go ahead.
Is there any like non-trivial map that we do have the tools to compute the degree for now? Because you're saying we're going
Well,
to see this later.
Later today.
Degree.
So
Oh, okay.
yeah, once I finish the properties, then we'll talk about how you actually compute it.
Okay. Okay.
Yeah.
That's what I was confused for.
Okay. Yeah. But this is the intuition you should have.
Okay.
That it's just how many times are you wrapping around, taking orientation into account. So this has degree k for any integer. So if you have c to the -2, you get degree -2.
Can we extend that example?
Yes. So also, if we have time, we'll do it today. Okay, so the next property is that the degree of a composition is equal to the product of the degrees. Okay. And so this is just because the induced map from the composition is the composition of the induced maps. Right. So when you're acting on the integers, g star multiplies it by the degree of g, and then f star multiplies by the degree of f. So the composition multiplied by the product of degrees. Okay. Suppose f is, well, so let's put the sphere in Rn. So take Sn and put it inside Rn plus 1. So think of the plane cutting it through an equator. And if f is reflection across a plane through the center of the sphere, then the degree of f is going to be -1. So in this case, we have the coordinates, say, x0 to xn, and we're just mapping. All that f does is change the sign of xn. So without loss of generality, let's say that you're just changing the last coordinate, so reflection in the last coordinate. Okay, so here's how we're going to do this. Think about the case of the circle. We have a map that just flips the y coordinate, right? And we want to know what this does to homology. So one way of seeing what it does to homology is put a delta complex structure that has those as the vertices, and then you have the upper interval and the lower interval. So and same thing over here. For higher dimensions, make this U and this L, and these can be the images of n simplices for Sn. So Sn has a delta complex structure with two n simplices, U and L, and Hn of Sn is generated by U minus L. right, the way I've drawn it. L minus u, the way I drew it. Yeah, let's put the arrows going that way so that it's true. So nice. But f star of u minus L is L minus u. Right, or if you like F sharp. That's what it's doing at the chain level. So the degree of f is equal to -1. Okay, so there's a non-trivial degree. We can use this computation and the previous property. See, let A be the antipodal map. The degree of A is equal to -1 to the n plus 1. Yep, plus 1. Right? And that's because A, in coordinates like these, would take x0 to xn and give you -x0 minus x1 minus xn. So it's just the composition of n plus 1 reflections. Right? You just reflect in every coordinate. Okay, so an easy consequence is that if n is even, then the antipodal map is not homotopic to the identity map, right? Because they have different degrees. This has degree -1, and this has degree 1. Okay. If f has no fixed points, right, i.e. ff is different for x for every x, then the degree of f is equal to -1 to the n plus 1. So just take f sub t of x to be 1 minus t f of x minus tx. Right? This is never equal to 0. And if I divide by its length, then it always maps into the sphere. So it goes from the sphere to itself, and it's a homotopy between if t is equal to 0, you get f, and if t is equal to 1, hold on, I have a sign wrong, don't I? No, if t is equal to 1, you get minus x, which is the antipodal map. And so this is a homotopy between f and a. So they have the same degree.
We get as a consequence of this that entity map has to have a fixed point.
We do. Okay, so let's look at the consequence for vector fields on Sn. Okay, so Sn is an n-dimensional manifold, but it, of course, it's better than that. It's a smooth manifold, right? It doesn't just have neighborhoods that are homeomorphic to neighborhoods in Rn. When you look at what are called transition maps, so what happens when you go from one of these neighborhoods to another one of these neighborhoods, the transition maps are smooth. So that means that it makes sense to talk about smooth functions, and if you can talk about smooth functions, you can talk about their derivatives. So their derivatives give you vector fields. So a vector field, so we can be very explicit here. So Sn sits inside Rn plus 1, and the tangent space at a point x in Sn is all of the vectors in Rn plus 1 that are orthogonal to x. Right, so you have the sphere sitting inside Rn plus 1. At every point, you have a tangent plane in this case, right, in the case of S2. And that tangent plane just has as a normal vector the position vector of that point. Right, so it's always orthogonal. Right, and that, of course, is because the sphere is just all of the points such that x dot x is equal to 1. So if I take a derivative, then I get x dot plus x dot is equal to 0. So that's 2x times x dot equal to 0. So x and x dot are orthogonal. So anyway, as you saw in calculus, the tangent plane to the sphere is just the orthogonal vectors to that point. So a vector field is just the any function, a vector field, to, well, we can go ahead and say Rn plus 1, but I really want v of x to be in Tx Sn. So what I want is that v of x dot x is equal to 0.
Wait, sorry, can you go back to, I'm confused about these equations on the bottom of the.
Yeah, so I'm just reminding you why the tangent vectors to the sphere are orthogonal to the position. And that's because the sphere is defined by x dot x equal to 1, right, with the usual dot product, right? And if you just differentiate both sides,
Okay.
then by the Leibniz rule on the left, you get this, right? But that just tells you that x is orthogonal to x dot.
So it's equivalent to saying that any line through the origin is normal to the sphere.
That's right, where it intersects, yeah.
And sorry, what is the notation with the dot on top of the x?
Oh, the tangent vector.
Oh, okay.
Yeah. So just a derivative. Okay, so that's what a vector field is. So what do these look like? So for example, when n is equal to 1, then you have the circle. And at every point, well, you have the tangent line in this case. So I just have to pick a vector on this tangent line. So for example, I can just have something that's going around this way. Right, that's what a vector field would look like if you're going that way. On the sphere, well, you could imagine that the wind is flowing to the east, directly east everywhere. So it's going to have to vanish at the North Pole for that to make sense, for it to be continuous. And also at the South Pole. Right, so if you think of something that's flowing always east, then of course when you get to the North Pole, there's no good choice for where to go, so it needs to vanish. It's going to be continuous. Right? You could also imagine something more interesting, like you have a point here, and you have things flowing away from that point. So think of flow lines like this. And then similarly, coming down here. Of course, if I could draw, they would not intersect.
Wait, so what are these supposed to be?
Oh, this is just which way
Okay.
things are flowing. So we have this point where it vanishes, and then near this point, things are flowing away in circles like this. Okay, so you know, vector field. So we talk about this in calculus, right? What does this have to do with degree? Well, here's the theorem. If Sn has a vector field that never vanishes, then n is odd. Okay? So in those pictures, in the case of n equals 1, we have a vector field that never vanishes, right? It just says keep going forward. Right? But when we got to n equals 2, both of the examples I drew have places where it vanishes. Right? The first one vanishes at the North and South Pole, and the other one vanishes at that point in the center. So that's not just lack of creativity on my part. In even dimensions, any vector field has to vanish somewhere. Okay. So given our vector field is a map from Sn to Rn plus 1, if it's never 0, let v tilde of x be v of x normalized to have length 1. So now v tilde is going from Sn to Sn. So consider the following homotopy. So let's do cosine of pi t x plus sine v tilde of x. So here ft takes points on Sn to points on Sn. Right, because cosine squared plus sine squared is equal to 1. And well, because cosine squared and sine squared is equal to 1, and x is orthogonal to v tilde of x, so that I only need to check the coefficients. So f0 is cosine of 0 is equal to 1, sine of 0 is 0, so this is x, and f1 of x is equal to v tilde of x. Yes?
So shouldn't the coefficients be pi over 2 then?
When I put 1 sine of pi over 2. Pi over 2 would work better, wouldn't it? Or 2 pi. No, 2 pi would not work. Pi over 2?
And also, are we requiring a vector field to be continuous as part of the definition?
Yes.
Okay.
Yeah, smooth even if you like. But yes, thank you. So let's put pi over 2 so that indeed at 1 we get v tilde of x. So,
Define what smooth means.
well, here we have a map from part of Rn plus 1 to Rn plus 1, right? So smooth means that you can extend this to some open set, and then you get a map from Rn plus 1 to Rn plus 1, and that is smooth, right? So yeah, smooth on a closed set always means that that there is some open neighborhood, and you have a smooth function from that neighborhood that you've restricted to your
I don't
closed
even
set.
think I know what smooth function means.
Sure. So if you have a map from Rn to Rn, then in in coordinates, you just have maps from Rn to R,
Okay.
right? And smooth means that you can take all of the derivatives you like.
Okay. Okay.
C infinity even?
Yeah. Yeah, so by smooth I always mean C infinity.
Okay.
Yeah. Okay, so the degree of v tilde of x is equal to the degree of 1 of the identity. Hold on, F1. Yeah, so, okay, hold on. So let's keep going with this homotopy. So, okay, well, now we've put pi over 2, so that's v tilde. So if we put f of 2, then when I get pi, cosine is minus 1 and sine is 0. So this is minus x. The antipodal map.
Is F a homotopy?
F is a homotopy.
But it's one more than just.
Well, it is because I changed this. Really, I should have kept it here.
Okay.
Yeah. There we go. The point was that I needed to keep going all the way to 1 to get the antipodal map, right?
So, okay.
Right, because really the punchline isn't what happened to v tilde. The punchline is that the identity map and the antipodal map are homotopic. Right, so 1, which is the degree of the identity map, is equal to the degree of the antipodal map, which is minus 1 to the n plus 1. So n has to be odd.
Does the converse hold? That is to say, if n is odd, can we find a vector field that never vanishes?
Yes, we can write it down. So if n is odd, then this maps to minus x1, x0, minus x3, x2, minus xn, xn minus 1. Restricts to Sn, and nowhere vanishing. Not. Yeah, so there it is. Yes?
So does this generalize to things other than spheres?
It does, but not immediately. So if I give you any map between manifolds of the same dimension, then there is a degree assigned to that map. But it's not obtained by looking at the top homology group of the manifolds, because those might not just be Z. Instead, you do something which we're going to do very soon. So I have one more property to show, and then we'll figure out how to define this degree in general.
And presumably this theorem doesn't extend to arbitrary manifolds because, for instance, on a torus, which is a 2-manifold, you can get a vector field that never vanishes pretty easily.
That's right. That's right. So it turns out there is a generalization that, that does extend. And yeah, in fact, even if I don't have time today, next class I'll talk about it. As a digression, because we're not going to prove anything. Okay, so here's a property. If you have a group and it acts on Sn freely, so remember that means every G acts, defines a homeomorphism. That's what it means to have an action, and product goes to composition. And that it's free is that if G of a point is equal to a point, then G is the identity for some. Okay, so that's what we mean by G acts on Sn freely. And n is even, then G is very limited. It is a subgroup of C2.
There aren't a lot.
There are not. Okay, so why is that? Well, G has an action, so we have a map from G to the homeomorphisms of Sn, right? That's our action. And then to every homeomorphism, we can assign the degree. Okay, the degree of a homeomorphism is always plus or minus 1. So I wonder if I was supposed to have said that. Okay, well, how do we know that? Well, homeomorphism has an inverse. So you have to map into the invertible elements of the integers. And the invertible elements are just plus and minus 1, right? But I think I probably should have mentioned this when we talked about how the degree of a composition is the product of the degrees, that any homotopy equivalence would have to have degree plus or minus 1, just because it has an inverse. Okay. So G maps into there, and if since the action is free, the degree of G. So remember, we showed that if G does not, if any map doesn't have a fixed point, then it has the same degree as the antipodal map, right? So if G is not the identity of G, then the degree of G has to be the same as the degree of the antipodal map, since there are no fixed points. Right? The degree of the antipodal map is minus 1 to the n plus 1, but since n is even, this is minus 1. So if G is not, if little g is not equal to the identity, then this map, which is composition of homomorphisms, maps to minus 1, right? So that means that this map is injective, because the only thing that goes to the identity is the identity. So call this map phi.
Can you explain again why the degree of G is equal to the degree of the antipodal map?
Yes, so one of the properties we proved was that if you have a map between spheres that doesn't have any fixed points, then it has the same degree as the antipodal map, right? Because we could just write down a homotopy between it and the antipodal map. And acting freely means precisely that you don't have any fixed points,
Okay.
right? So it doesn't have any fixed points, so it has this degree, -1. Right? So phi is injective, right? So if phi is injective, then it's an isomorphism onto its image.
Why does that show that phi is injective?
Because remember, for a homomorphism, we just have to see what elements get sent to the identity, right? And this shows that the only element that gets sent to the identity is the identity. Okay. So how do we compute the degree in practice, right? So unless you're able to homotop it to the identity or the antipodal map, or it's a reflection, then we don't have any way of computing it. But the degree actually is something that's very computable. So here's what we compute. In practice, we compute the degree. By first finding y in Sn such that f inverse of y is finite. Okay, so let's set aside for a moment why can you find such a point. And let's just say that we were handed such a point, and then we want to compute the degree. Okay, so since Sn is a manifold, I know that every point has a neighborhood that looks like a neighborhood of the origin in Rn. Right? So pick neighborhoods. So pick neighborhoods v of y and ui of xi, so that with the ui disjoint, well, let's say ui of j is equal to empty set of I from j, and all homeomorphic to some neighborhood of 0 in Rn, and such that f sends ui into V. So let's right, so I'm not asking for homeomorphism, just it lands inside V. Okay, so you can always do this because being a local homeomorphism means that if you give me any neighborhood of a point, I can find some smaller neighborhood that is homeomorphic to an open subset of Rn. Right? So, well, in some neighborhood, we can even choose these to be, a ball around the origin of whatever size you like, some small enough size.
So are we doing this for every point y?
Well, no, we have some point y that has this property.
Okay, and after this, we're going to figure out why there is some y? Or?
Well, yes. So I'm going to wave my hands because the reason is if things are smooth, then you can always find these points. In fact, almost every point will work. But it is a property of smoothness. And so it's unfortunately beyond the scope of the course.
Okay.
Okay, but let's say you do this. Then, then you could look at the local homology. So Hn of u minus, so ui xi. So f will map this into Hn of v minus y, right? Because we know that f maps each xi to y.
What does that say? Hn is
Ui, comma, ui minus xi. And then v, comma, v minus y. All right? So these are the local homology groups, and we know that these are just C's. So we get a degree from seeing what this does to a generator, right? So this map is given by 1 goes to, and we're going to call this the degree at xi. So it's the local degree. Okay, so what we want to show is that the degree is given by the sum of these local degrees. Okay. So we want to show degree of f is equal to the sum over all of the inverse images of this y of the degree of xi. Yes?
So the local degree can be viewed as sort of like the multiplicity of xi as a preimage of y.
Well, so the multiplicity, not quite. It's more like the local degree is something that you can compute with linear algebra in practice. So it's, once you have a smooth map, so if you have a smooth map, you can pick these. So the local degree is always going to be either plus or minus 1, just depending on whether or not f preserves the orientation at xi or reverses the orientation of xi. So
But
each
it
of
could
these.
be-
So
there
yeah.
could be a sign change there.
That's right. So,
Oh.
but it's just going to be preserve the orientation or not preserve the orientation. And that's why it's usually very easy to compute the local degree. So you just look at it and you can compute the local degree if you can draw the map. But in any case, we'll just take it as a given that this is simpler than this, so that this is a win. In practice, it is. So, okay, we want to show this. But instead of rushing through it in 6 minutes, we'll just do it next time.